Okay, what's really nice is that because of this first question too, I think that's going to cover a lot of things that we're going to talk about in interaction. So I'm not going to even dwell on that. So, all right, so going now to interactions, right? So improving linear regression. So there's two things that we talk about in the curriculum in particular, polynomial regression and interactions. So I think it's nice to kind of talk about polynomial regression. So first of all, we say, okay, we have multiple linear regression, which the equation looks just like this. So I have y hat equals w0 plus w1 times x1 plus w2 times x2. And these w's right here just represent just some numbers, coefficients and intercepts. I call them w because later on we'll talk about it has to be weights for other machine learning models. But just kind of know it's like this is just saying, oh, it's some number, right? And so I can actually write the whole thing out like y hat is equal to the sum of these numbers, whatever that number is, times xn, where xn is going to be some feature, right? The first feature, the second feature, the third feature. And by default, we just say xn or x0, it's just 1, right? It's just the y-intercept. But the rest of these, like x1, x2, x3, could be different features. Okay, everyone sound pretty good review, right? This is like just what multiple linear regression looks like. And just a quick thing is like it's linear because this right here is going to create like a multidimensional, like, linear model. Essentially, it means that, oh, we can project this down straight to a line, essentially. It's analogous to, it's a good analogy to a line, right? So anyway, so this is linear. So what's kind of cool is like, well, okay, we can take this whole thing here and just make it more complex. So the way we can do this is essentially like, well, let's say, we have xn. Well, xn is just some feature. So we can actually consider like something that's a little more complicated like this. Instead of adding new features, like we have temperature and then let's say yield, whatever, I just pulled this, I don't even remember where I pulled this off of. But basically just an example, right? Is that if we have this guy, this could be like, okay, like we could maybe pull up more features like besides temperature to help explain this target yield. But we can also use just more, basically more information from temperature. So in this case, we can actually say, well, let's just do a linear model, but instead of saying x1, x2, x3, we essentially say, well, we can actually use the polynomial definition. So we say that, well, x1 is just equal to x, right? x2 is equal to just x squared, right? And then you can kind of like keep building that up if you want. And hopefully that kind of makes sense. Like if you look at this kind of equation and this equation, they're essentially the same thing. It's just that we defined x1 as x, x2 as x squared, and so on. Okay, does that make sense? And so we can just write it out, for example, like, oh, y hat is equal to, this thing, like where we have n different powers, right? We could go on forever, but that's not great because computers don't do good for with infinity. So we cap it off at some value ends, let's say like to the power of 10 or something like that. And then we can say, okay, now we have a linear regression, right? And we can fit those linear regression then, just like this guy. We know how to fit this, and we can then determine what's the best line that fits on here. So in this case, I actually showed two examples where maybe you only use, up to x squared. So you get kind of like more parabola. And then maybe you use something like closer to like x to the power of 5, where you get these extra, curves and stuff like this. So you get a polynomial. And so it's kind of cool. It's like, even though this is more complex and it's a polynomial, all we did basically is use the fact that we know how linear regression works and just say, hey, this is going to be a polynomial term. And that's how we kind of fit that in there. Does that make sense to people? Like this connection here to like something like this? Yeah, give a thumbs up.
And in this case, we're still one-dimensional. We're not multi-dimensional, right? Because we're only using one feature.
You say we have one feature, yeah. Like I would argue is that we are doing multi-dimensional because the other dimensions are just higher powers of that one feature. So you can kind of say one-dimensional, but really like not, like, right? Like you're using one feature. But yeah, I think that's what you meant, right, Alvaro? Okay, cool, he nods. All right, so yeah, so what's kind of nice is that we can say, okay, like, well, now we can actually expand this further, right? So like Alvaro kind of like, Alvaro, you do a really great job like leading into the next point, because the next one basically is like, well, okay, this right here is kind of like our just one dimension, right? Our one feature, and then we use polynomial terms. And this x2 right here, well, this x2 can be like maybe another feature, right? And do the same exact thing, right? So if I were to expand, like if I were to summarize it, I'm like, really nice math, like you're like, oh, look at this beautiful short equation. What this really is showing, and I'm just going to quickly as I can write this out. Essentially what this is y hat is equal to, just put like beta 0, right? And then I guess technically 0, 0. And we have like, x1 plus, you should have constants in front, but I'm being lazy. x1 squared plus x1 cubed. And we go on however many times, right? And then this is plus x2 plus x2 squared plus and so on. Okay, does that make sense to everyone? And then you can do this, for however many features. If you have 3 features, you have like x3 down here, right? And I'm writing it like in this funky way, but you can imagine just writing it all like one line, like straight across. Okay, all right, so that makes sense to everyone. And you can see is that it's just linear regression, right? It's multiple linear regression, except some of those terms are now, squared terms. So you can kind of think this as well. I think I have a little discussion here. Oh, okay. Hold on to that for a second. You can kind of think of this as being like if you had like your data frame drawn out. Your data frame, let's say you only use temperature, it would be like, oh, this is temperature T, and this is like some values right here, and then you'd have T squared here, right? And then values written out here, and then T cubed here, right? And then you can imagine getting each of these values from the next one. Like in the end, your model doesn't care what these things are. They don't care if it was T squared. It just says, oh, that's a new feature. Like it could have been whatever you want. It just happens to be the squared of this original value. Okay, sound good? Cool. All right, and then I had a little discussion here. Won't take too long here. Okay, there's no limit on the polynomial degree. Oh yeah, you can use as many as you want to, but there's a caveat to that. You probably shouldn't use a huge amount because you can imagine now if we have like 3 features here, right? At first we only had like, oh, there's only 3 different features. And first of all, it's like, oh, what features should we use, right? There's so many combinations. It's like, oh, we use both of these things. Do we use one of these things? Do we use 2 of them, right? There's, oh, like which 2 do we use? So you can think like there's about technically 6 different models you can build from this. If you say now they each can have up to 10 other terms, well, not all of those terms, like 10 polynomial terms, so like x1, x cubed, x squared, all the way to x to the 10th. If you do that for each one now you have 60, right? So we have like all these different possibilities. Well, not 60 now. We have all the different polynomial terms, which technically now there are 30 different terms. And then you can do how many combinations can you make of those 30 different terms, right? Which ones you can keep out. And you can imagine that starts getting pretty big. And that's just with 3 features. So one thing in general is that you might want to consider starting simple first and then trying to go more complicated if there seems to be extra structure that needs to be done. You can just try to blindly go for it and see how well it does. There are some parts, I will tell you that curriculum doesn't really show you this part, but like there are things in sklearn that you can say, hey, try to use polynomial terms. And it's actually really straightforward to like call it. But still, you don't want like, like in general, maybe to the power of 3 is probably good enough. Like there's very few times where like it makes more sense to have higher powers, but you never know. Let's hear any disadvantages is that it makes it more complicated, right? Is that if we can build a simpler model that does just at least nearly as well as a more complicated model, we want the simpler model. Why is that? Why would we want a more simple model than a complicated model if it does about the same?
So it passes the testing.
I'm sorry, say that one more time.
So it passes the testing phase, so it's accurate in testing.
Yeah, accurate in testing, meaning that it generalizes well, right? So if we have a more simple model, it tends to be a little bit easier to generalize than a more complicated model, because the complication, remember, is coming from the fact of the data that we've seen. So basically, by making it more complicated, you are trying to fit this model onto data you've already seen, where you want it to generalize to the testing set, and other data sets that it's never seen before. Usually it makes more sense than to keep it simple. That way it doesn't try to become overconfident and overfit. Okay, cool. Any questions on this guy then? All right, cool. So interactions, I'm going to go really quickly. We talked about this example right here, so I'm not going to kind of go through it again. But basically the main thing you should think about like interactions is basically when another variable combined together makes a new like thing. And so I kind of mentioned about like different origins, right? Like let's say North America, by default makes really inefficient cars, or like inefficient compared to like Japan or something like that. But as we increase in horsepower, they can make pretty good, efficient, like more efficient cars as they can higher horsepower compared to Japan, where Japan's really good at having lower power and stuff like this. So maybe, for example, that can affect the miles per gallon. And so, I think the curriculum does a good job of talking about this. I'm not going to go through the whole part, but basically it's that it's not the sum of their parts, what linear regression relies on, right? It relies on the fact that each feature is independent from each other, right? So interactions are things that combine together. So that might be something you consider. And usually kind of a really good gut check is just to think like of the features and just say conceptually, like, does it make sense? Like, does it seem like these two features would interact in such a way that they would kind of create a different kind of result? That's kind of a good way. But then also you might do this where you might literally just try it out and see how well it does. Okay. Kiva, yeah.
Yeah. Mathematically, how does an interaction term affect your model?
Can you go a little more detailed than that?
Like, it raises your R squared, right? An interaction term.
Like adding a new interaction term.
Interaction term, yeah.
Mm-hmm.
So like mathematically, I understand that whenever you add a new term, it raises your R squared, but specifically when you add an interaction term, why would that raise the R squared?
Yeah, so basically for the record is that adding any random feature will increase your R squared because there's a chance, even if it's completely unrelated to your data or your situation, by chance it's going to explain a little bit more about
it'll fit a little bit better, yeah.
Yeah. And so hopefully, this is why you don't want to just add all the interactions terms, say, oh, my R squared's so good. And it's probably like, well, it's probably because it's overfitting, right? This is why we use the testing set and cross-validation and such. But another way you can think of like the way it might actually be helpful, like legitimately helpful, not just making R squared better, is that by itself, like if we consider them independent, that's where we get those linear regression parts. If we consider an interacting term, you basically have like, oh, there's this extra factor where I'm trying to think of a good scenario off the top of my head, but I can't, unfortunately. But like you can think of as like, oh, these two together are going to like kind of super boost this or super subtract it and stuff like that. I'm trying to think of a good example of this and I really can't. I'm sorry. Probably should come up with something. But real quickly, the reason why I want to just bring this up, and I'm just going to do it really quickly, is that this interaction term is just essentially just like how we did with polynomial terms. It's just a new term that we add into our linear regression. So it's still a linear regression, just like this guy. But now like, for example, like this x squared term, let's say this x2, let's say like we have x1 and x2. We now have something like x3 is equal to x1 times x2. So that's our new feature now, right? It's our interacting feature. And this is why also like Jessica had mentioned about like horsepower. I think the curriculum's called it like horsepower _ origin is their new feature. And that's the way you can really think about it. It's like, oh, it's just a new feature that we're considering. Okay, so we can still use the same exact linear regression, strategy of like basically fitting the data onto this new feature and the other features. Okay. One quick thing too, you can also still have powers in here as well. So you can see how quickly this can get like really complicated. It's like now we can have powers of interaction parts and stuff like this. And the number of features you can possibly have become huge. There's actually a real issue with this is that if you have too many features, you can, for the record, like always solve, like you can analytically solve. You guys know what analytically solve means by chance? Give me a thumbs up if you guys know what that term means, maybe not. Analytically solve just means that you can write down the equation. Like, like solve for X. Like if you imagine like, it's like, oh, like back to algebra stuff. You have something like y equals 3 plus x, something like this, right? Or let's say like 2. 2 equals 3 plus x. Well, we know x has to be -1. We can analytically solve this. We can say, oh, we can actually solve this with algebra and figure this exact thing out, right? Where you subtract 3 on both sides, you get x equals -1. Some solutions cannot be analytically solved. For example, a famous one that's really simple, x equals sine of x. You cannot, as hard as you try, there is no algebra you can do to try to separate this out and say x is equal to something. You have to actually literally put this in like a numerical solution. You have to literally try to numerically figure out by essentially keep estimating until we get values that solve this. Because we can actually solve this equation, but you can't do it analytically. So linear regression you can always analytically solve the solution. Like you can always find it. Like you can figure out what the best coefficients are for the data. The caveat is that the more features you have, it goes up by about n to the power of 3. So if you have like 10 features, right, it takes, if you have, let's say you have 10 features and you go up to like 100 more features. So that's like times 10 more, right? This doesn't take 10 more times to solve. It takes 10 to the power of 3 to solve. So it takes 1,000 times longer and 1,000 times more computing power. So this is why as we get more features, we're like, ooh, this is not great. So this is why we actually won't solve in the long term linear regression with analytical solutions, because if you have 100 features, which is not a huge amount in data science, and you start increasing that, when you start like, okay, let me talk about interacting terms, polynomial terms, it gets really big. So it's a good idea first to really consider, do I need to consider all interacting terms, all polynomial terms, and all that stuff? Okay. Cool. Any questions? Yeah.
When I was doing this, I thought of like our last project, the movie industry analysis. It made me think of how some of them were interacting. I think it was like revenue, profit, and what was the other one? Revenue, profit, and something else, but they were like all interacting. So in that case, would we just multiply like all of them?
Yeah, you're saying like the features together. So like having, yeah,
Like
I mean,
3, yeah.
you could technically do it. And this is where like you can start like building up a whole bunch of interactions, right? You can have like x1 times x2 times x3, right? You might also want to consider, well, what about just x1 and x2? And what about x1 and just x3, right? And also like x2 and x3. So in general, this by itself is generally not used, just because this suggests that there's a very complex interaction between the two, where we'd like to see, well, can we simply just define it with just these kind of interactions right here? But yeah, you totally could. Like you could create this feature right here, and maybe it does have an interaction. Almost kind of like a rock, paper, scissors kind of like interaction, right? But in general is that I'm gonna steer you guys towards this direction, is that this is also a lot more explainable than like this guy right here. Because like now you have 3 different terms being multiplied together. And maybe this does make more sense. Maybe this does do a better job of making predictions. But if we can separate it out and say they're independent from each other, then it's like, okay, let's try doing that first. But yeah.
And then this might seem obvious, but I didn't see it done in like our labs. But so once we have, like, let's say those 3 are related, we find like 2 of them interact really well, that like describes or just does well in the model. So then would we remove like would we remove the 3 original variables then?
Yeah, so if you were to do something like stepwise selection, you can look at like p-value, for example, to see how well this actually does. You can say, okay, like for example, you can try all 3 of these, examples right here. And then if the p-value is too high in the sense that it's not significant, you can say, oh, let me just drop these, it's like, I'm only going to keep this one. Maybe that's the only interaction feature that actually matters. This is where, again, like we'll see like other machine learning models where like we can do a whole bunch of different things. The weird thing is like linear regression is probably the closest to like, we are trying to figure out the best way to make this model work. And we have to use like human intervention to make sure we don't take forever to like figure out this problem. If you could give a computer and say, hey, go ahead and try every single possible combination with what we can have, but it will literally take forever, right? So we kind of use hope, like usually linear regression is really useful when we can use our intuition a little bit and be like, well, okay, like what do we think is going to be expecting? And then only test those features and then see if our intuition matches up with how well the model does with p-values and r-squared values and all that good stuff. But yeah, in theory, you could do whatever you want with linear regression. But we'll find those machine learning algorithms. We offload the algorithm, like the work instead of us trying to figure out what the model should be. Instead, what we do, we focus on designing the algorithm to better pick those values. So there's kind of be like a little offload of like what we focus on. And linear regression is like, if you know really well what you expect to, linear regression might be just as good just to go for it. So yeah.
And thanks. And so then, like, if we were to combine like profit and revenue, and then those are what, like an interacting variable, would we then remove profit and also revenue from the model?
You probably would try to use it independent. So like in this scenario, x1 plus x2 plus x1 times x2. And you would still see if there is extra features. For example, maybe x1 and x2 do contribute, but then there's also a little extra bit that's coming in from the interacting feature itself. Or it could just be the interacting feature is the dominant feature that's making the prediction, right? And this is, again, where the p-value kind of comes in and being like, oh, is it making a better r-squared value? Is the p-value significant and stuff?
Gotcha. Thank you.
Yeah, no problem. Cool. All right. Yeah, any last questions on interacting features or anything we talked about today? Pretty good.